Hi, this is Mr. Ward, and I'm doing a video key for Do Now 14.2. So the first one is about flipping a coin. Now this is a compound probability. We're going to flip a coin 7 times. We're going to see if we get heads 7 times in a row. So the probability, what you're going to do is so there's only one possibility of getting heads when you flip a coin, and there's 2 actual possible outcomes. So the probability is like 1 out of 2 the first time you flip. Now the second time you flip, it's still 1 out of 2. And the second time you flip, it's still 1 out of 2. So what we end up doing is we have like these branches going off, heads or tails, then heads or tails, heads or tails. There's only one path out of all of it, 1 times 1 times 1 times 1 path out of all the 2 times 2 times 2 times 2, etc. paths. So we end up with this 1 over 2 times 1 over 2, etc. We call this a repetitive probability because each event doesn't affect the last one, so that nothing is changed in the situation. Okay, so we could write it out like this: 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2. I think I said 7 1/2s, but there's an easier way to do it and write it with exponents. Since there are 7 factors, the exponent we would use would be 7. So we would write it as 1/2, and put that in parentheses. The entire thing is to the 7th power, and 1 to the 7th power is just 1, and 2 to the 7th power is 128, and so there's your probability. Now, that last one was a compound probability because there were more than one event. So compound probabilities need to have combinations of events. Okay, so now we're going to select randomly the president, vice president, and treasurer of our mass transit system from the 6 students in the class. I've labeled you A, B, C, D, E, and F, so I won't have any bias about who I pick. And we're going to choose randomly. So when we start choosing, so after we choose our first one, so the first choice, there are 6 possibilities that we could choose from: A, B, C, D, E, or F. Once I've chosen someone, I only have 5 possibilities to choose from. So now in my second round, I have 5. In my third round, I only have 4. So my total number of possible choices is 6 times 5 times 4, which is going to equal 120 possible president, EP, and treasurer combinations. Okay. And there's actually a word for this. Rather than combinations, it'd be better to call this permutations, because permutations represent ways to mix things up where the order matters. This is counting where the order matters. Okay, and so it matters. I can't, we're not swapping around who's president and vice president. Whoever is president is sort of in charge. Vice president is in charge of the president. Gets a boo-boo and can't be around to do things. The treasurer has a specific job. So the order matters in this case. However, in this second question, in 3B, the order doesn't matter. You're selecting 3 people to be on a committee. They're all equal, and they're from the 6 students in our class. It's the committee for how big a train car can be. Okay, you're selecting randomly. So again, we're going to start with 6 times 5 times 4 possible initial choices. However, we need to divide that by the number of possible ways those 3 people could be arranged, because we could end up with A, B, and C as one of the picks. We could also end up with A, C, B, but that's the same committee. We haven't changed anything with A, C, B. We could also have picked B first, student B first, and then A, and then C. We could pick B, and then C, and then A. That's the same committee too. So now I've got 4 different ways that committee could be student A, B, and C. And now I could even start with C, and then A, and then B, and C, and then B, and A. So I now have 6 different ways that I could have selected. So when we think about the 6 different ways that we could have selected, we start off with 3 different ways, then 2 different ways, then 1 way the third person could be. So there's 3 different possible first letters. And then once you've chosen that first one, there's 2 different possible second letters. And then there's just 1 possible last letter. So we are going to divide our total number of people by 3 times 2 times 1. So that ends up equaling 120, 6 times 5 times 4, divided by 6. So we have actually 20 different ways to form our committee. Since the order does not matter, we call this a combination. There are 20 combinations. Combinations are a counting situation where the order does not matter. And both of these matter a lot when we're thinking about the numbers. It matters a lot when we're thinking about the total possible outcomes. So in probability, we have desired outcomes divided by total possible outcomes. Okay, you should probably spell that total desired possible outcomes divided by total possible outcomes. So when we're doing that sort of probability question, if we were figuring out what are the possibilities that a particular 3 students, A, B, and C, would be the vice president, and treasurer, there's actually only one way it could be A, B, and C. So it's 1 out of 120. But here, what we'd end up doing, if we wanted to find out how many different desired outcomes we'd have A, B, and C on the committee, well, there's 6. Okay, so the probability would end up being 6 out of 120 because there's 120 possible permutations. And so it ends up being 1 out of 20 chance that it's A, B, and C. I'm sorry. Yeah, 1 out of 20 chance that it's A, B, and C. Okay, so I hope that clarifies a little bit. We'll play around with this idea of order mattering and not mattering today. And also, we'll have a little time to play with maps of a public transit system that we could do. And we'll have some time to just work on our stuff. I hope this is helpful.